Okay. Good morning, everyone. Hopefully everybody had a good weekend. As always, what are your questions? Any questions arise over the weekend? If not, then we're going to talk about our electrical. And the way I like to get you excited about electrical is, by now you've been exposed to the cockpit. You've seen all our gauges, all our instrumentation. And I've got a question for you. And that is, how important is electricity to the CH-47D helicopter? How important is electricity to the CH-47?
It'll fly without it.
Huh?
It'll fly.
Well, yeah, has to fly, doesn't it? Okay.
It's important.
It's very important, but what confusion comes in hand? Okay, whether it was the TH-67, now the Black Hawk and the Apaches are starting to be just like us, okay, where they have a similar system that we have. And that is, up in the cockpit, we're used to having to have gauges to monitor. We're used to having switches to throw. And in this aircraft, except for the one electrical panel, you've got nothing to monitor, and you've got the one control panel. That's it. That gives you the ability to turn on a battery and turn off a battery, and 3 generators. That's it. Other than that, there's no output meters, input meters, load meters, amp meters, volt meters. There's no meters at all on this aircraft, kind of giving you the misconception that possibly electricity isn't as important because there's nothing for you to control and monitor. And that's a weird term for a pilot. You know, pilots like to control and monitor things. That's the basis for everything. But yet, on electricity-wise, we don't. Now, the second thing I'm going to tell you, if you think I'm going to make you electrical engineers, you're wrong. It's not my job here today. My job here today is to help you understand the electrical system as it pertains to the CH-47D. Okay, where are my electrical engineers? Do I have any? Okay, you're probably going to be our closest, but you're not going to raise your hand, are you? Okay. Now, normally, I apologize right off the get-go. Why? Because sometimes, in order to simplify things, I cut it down to the very, very basic that you need to know. Okay? By the time you walk out that door today, you're not going to be electrical engineers. Don't pretend to be. Don't want to be. Okay? That's a 5-year degree. Sometimes people push it even longer because it's complicated. We're going to keep this as simple as possible. That's my job. Now, the first thing I like to do before I even mess around with slides is do some definitions of terms. Okay? i.e., we refer to a bus. And we're not talking about the big bus here. Okay? We're talking about as it pertains to electrical system. Now, when we say buses, normally the first thing that comes to mind is this big yellow thing that transports students, right? So what is a bus? Now, here we go. A bus, quite simply, is nothing more than a means. And what it does is allows us to hook several components / systems to a single power source. Fair enough? That's all a bus is. You know, we're going to talk about a generator failure with a bus tie, a rectifier failure with a bus tie. We're going to talk about a generator failure without a bus tie, a rectifier failure without a bus tie. Okay? And the big thing about that is, what are we talking about? A failure, and by the way, PS is just power source. Why? Because this pertains to both AC and DC. It doesn't care. Fair enough? Now, what are we talking about in the case of a bus tie? All we're talking about is if this power source fails, the electrical system on the CH-47 has the ability to allow that other power source to pick up its load. That's all we're talking about. Up until now, most people were happy that if you could tell them that a generator failure or a rectifier failure with a bus tie results in a single light. Right? Either the generator or the rectifier, depending on which one we're talking about. A generator or a rectifier failure without a bus tie, the result was we got several lights. By the time we're done today, you're going to know what lights, why those lights, and not only that, you're going to know why we're landing this aircraft. Good? Now, the next term that comes in that a lot of people get confused, and we're going to emphasize it here again in just a second, is everything on this aircraft is AC operated, DC controlled. Matter of fact, this aircraft in the 714 configuration has one DC motor. And that's on what? Anybody remember? In the 714 configuration, this aircraft has one single DC motor. Your windshield wiper. Your windshield wiper motor is a reversible DC motor. That's all it is. Now, in the 712 configuration, you have 5 of them. And the 4 we're not going to talk about on a normal basis because why? As you can see, we got rid of the 712. We don't talk about it at all here. But your N1 actuators, 2 of them are reversible DC motors, and your N2 actuators are reversible DC motors. So 2 motors on the number 1 engine, 2 motors on the number 2 motor engine, plus your windshield wiper for 5 total. Other than that, everything else is going to follow this rule. Now, in helping you understand it, this is my AC power source, right? The goal is to get that power from point A to point B being a component or a system. Everybody agree with that? Okay. Now, what you're going to have through this process is a DC switch. So in order to get that power from point A to point B, this switch has to close to allow that to occur. Agreed? Now, why would it be important as pilots in this aircraft to understand that everything on this aircraft is AC operated, DC controlled?
If you can't switch it, you can't operate.
Exactly. So what? It's a no-brainer that if the AC power source goes away, we're going to lose the component or system. Agreed? That's a no-brainer. The concept that we forget about is because everything on this aircraft is AC operated, DC controlled, even if the AC power source is just fine, if this DC switch fails, the result's going to be the same. We're going to lose the components of the system. And that's why it's important, and that's why we beat that term into you over and over and over again. Everything on this aircraft, AC operated, DC controlled. Why? Because whether I lose the AC power source or the DC control, the result's going to be the same. I'm going to lose the component of the system. Any questions about that? Now, why do we front load this? Because as we go through this process of talking, now it's going to add some knowledge that you need, so as we go through this, it's going to be more understandable. Any questions so far? If not, then let's get into this electrical class. Terminal learning objective, action, describe components, operational characteristics, functions, and limitations of the CH-47D electrical system. Conditions, in a classroom given a CH-47D electrical system trainer, electrical system diagram, and student handouts. Standards, correctly answer in writing without reference 5 of 7 questions pertaining to the components, operational characteristics, limitations, and functions or malfunctions of the CH-47D electrical system in accordance with TM 1-1520-240-10 and your student handouts. Safety requirements, none. Risk assessment, low. Environmental consideration is none. Evaluation, each student will be evaluated on this block of instruction during the third written examination. This will be a criterion type examination requiring a go in each scored unit. You will have 90 minutes for the exam. Questions? All right, as we look about the electrical system, learning step activity 1, describe the operational characteristics, functions, and components of the electrical system. This outline is going to follow the same as what we've been doing in all the other classes. We're going to kind of look at it from a pre-flight perspective, and then we'll go into how the components work. Again, we got an AC electrical system, DC electrical system, keeping in mind what? Everything on this aircraft is AC operated, DC controlled. As we look at the AC electrical system, here's where I like to get you incredibly excited right off the get-go. Why? Because the power starts in the same spot, it ends in the same spot. It starts at your overhead control panel, located on the overhead panel, bottom left-hand side, marked electrical control panel. From there, through a series of components and systems, all that power is going to end up going to your power distribution panel for the process of what? Being distributed throughout your aircraft. In the case of the AC electrical system, you have your left and right electrical pods located at the very front of your fuel tanks, directly in front of your forward left and right auxiliary tanks. Where it starts to curve and go back into the airframe, you have that access panel, that is your electrical access or electrical pod. Now, everything is broken down how? Just like it's supposed to be. Left electrical pod belongs to the number 1 electrical system, right electrical pod belongs to the number 2. In the left electrical pod, you have your external power control unit. You have a generator control unit for the purpose of what? Gentlemen, this is what makes your job easy. Okay? This is what is actually controlling those generators and monitoring those generators for you. That's why you have nothing to monitor up in the front. These control units, these generator control units are doing it for you. So how many control units are we going to have?
3.
4. 3 that you're going to be concerned about. What's the one that we always are going to forget?
The external power?
The external power. Why, Jeff?
It's not on the aircraft.
Huh? But there's a component on the aircraft that you're going to be required to understand and explain and see. Okay, so why not? Because we do not use our external power source to crank this aircraft up. The only time we ever use the external power source is to facilitate maintenance. Okay, translation, we're not going to go out there, hook up the external power source, crank it. Okay, it's cranked, generators are on, disconnect it. We're not going to do that, not on a routine basis. Now maintenance, when you become a maintenance officer, you might. Okay, and until Korea this last time, I could honestly tell you that I had seen the external power source 3 times, and I had only cranked it or hooked it up to the aircraft 1 time. In Korea, we used it a little bit more, but I was in an AVM company. Okay, but other than that, it's not something that we use a lot. But it is an external, it is a power source. Why is that going to be important? Because when we talk about these systems, you do have to understand the relationship between the aircraft systems and that external power source. And we'll see you'll see what I mean about that here in a little bit. Okay? So in the right electrical pod, we have 2 more control units. Which control units were in the left electrical pod?
Number 1 and external.
Number 1 and external. So what's going to be in the right electrical pod?
Number 2 and APU.
Number 2 and APU. You see how they broke that down? Now I'm going to tell you firsthand. The APU gets a little bit confusing. Why does the APU get a little bit confusing? Because the problem is all the pieces and parts are associated with the number 2 side of the aircraft. But it actually powers up, as per your schematics, the number 1 side. And we'll make some more sense of that. But reality is, the APU generator gets a little bit confusing, only in the fact that everything for it is on the right side of the aircraft, but it powers up the number 1 PDP, the number 1 electrical system. And then we have 2 main generators and the APU generator, any one of which is capable of powering up everything this aircraft needs powered up. Okay, as we look at the main generators, they're going to be mounted to our transmission, so they're going to be available when rotor blades are turning. The APU generator is mounted to the left side of the APU, and therefore is going to be available anytime the APU is running. Any questions about that? Now, primarily, as we look at the main generators, we got a number 1 generator, and we got a number 2 generator. Okay? Reality is the number 1 generator primarily powers up the number 1 electrical system. Number 2 generator powers up the number 2 electrical system. But keeping in mind that in case of an emergency, either one of those generators can pick up the load for the other. And the APU generator, we know during start process, is going to power up both systems. And we'll talk more about that here in a little bit. And then we have our power distribution panel, and on that power distribution panel, we have our AC bus tie, commonly referred to as the gang bars. But this is the panel, and this is the system that allows for that automatic switchover to occur. Okay? Now, we can complicate this, or we can keep it simple. All the AC bus tie does, all the gang bars do, is allow for a single power source, in this case to power up both the number 1 and number 2 AC system. And notice I didn't specify directions, I didn't do any of that. Okay? That AC bus tie system, quite simply, allows any one of the single power sources to power up both the number 1 and number 2 AC systems. Any questions about that? And there's your external power source. Keeping in mind, the external power source, we're going to show it to you twice, but reality is it's the same external power unit for both AC and DC. It's the same auxiliary ground power unit that you saw for what? When was the first time you actually saw this? Under hydraulics. Okay, what we have now is a system that's very complicated that can provide for a lot of different things. Which means what? Which means later on when we start talking about the external power, we have to remember that because it's usable in a lot of different facets, it has a lot of different settings, a lot of different adjustments, and if those adjustments aren't right, the aircraft has to be able to protect itself from it. And we're going to talk about that as we go along. Looking at the DC electrical system, again, where it starts and where it ends is the exact same spots. It starts at that overhead control panel, and it ends at the power distribution panel, where from there on, it gets distributed to all the different components and systems that need that power. Again, as we look at it, we have 2 transformer rectifiers, one in the left electrical pod, one in the right electrical pod. The number 1 transformer rectifier powers up the number 1 DC system. The number 2 transformer rectifier, located in the right electrical power pod, powers up the number 2 DC system. In the left electrical pod, we have our battery, keeping in mind, how many battery systems do we currently have out there right now? Two, we are going to talk about both battery systems. We're going to talk about the NiCad battery, nickel cadmium battery, and we're going to talk about the sealed lead acid battery, slab battery for short. They're denoted by their color difference. That's the first thing you're going to notice. You got a blue battery, that is your NiCad battery, your nickel cadmium battery. And then you have your rose, your pink, your magenta, whatever it takes to help you in your masculinity describe that battery. And me, myself and I, it's a pink battery. There's no way to sugarcoat it. It is a pink battery. That is your sealed lead acid battery. Now, with the nickel cadmium battery in that same electrical pod, you have a battery charging system. Now, here's the problem, gentlemen. It's a turquoise battery charging system in color, but it goes away for the sealed lead acid battery, the slab battery, giving you the false impression that what? If the battery charger goes away, it kind of leads to the misconception that what? The sealed lead acid battery does not need to be charged. That is a bull-faced lie. It does need to be charged, and we'll talk about how that battery charges. Any questions about that? And then you got the battery relay, keeping in mind. Here we go. There's another one of those terms. Relay. Relay is nothing more than a fancy-dancy term for a switch. That's all it is. What's the complication? It's a multi-switch. So what you're going to find out is through this relay, we're going to talk about our different bus systems. Meaning what? Again, what is a bus? It's a means to connect several components and systems to a power source, a single power source. In this case, we're talking about the battery. Now, we could talk about relays for days and days and days. But you notice we haven't. So why are we going to talk about this relay? Because it's a big hunkin' relay in plain sight. And because it's out there so you can see it, so you can point to it, the IPs are going to ask you about it. And we're going to make sure that you understand it. Okay? Any questions about that? All right. The battery supplies the power for some DC for the following processes. APU start, emergency, and pressure refueling. That's what we use our battery for. Okay, and what you're going to find out is we have 5 DC bus. And we're going to break them down and help you make sense of them. Here's your left electrical pod to your left, the right electrical pod to your right. Left electrical pod is going to contain the transformer rectifier for the number 1 electrical DC system. The right electrical pod is going to contain the transformer rectifier for the number 2. The left electrical pod is also going to have your battery in it. Whether it's the NiCad battery, the nickel cadmium, or the slab battery, it doesn't matter. Both batteries are in the left electrical pod. And you can see that this is the slab battery, meaning what? Meaning that turquoise battery charging system has gone away. In its place, they put another relay. Any questions about that? And we will go over it. And just like before, what other electrical DC system do we have? We talked about the battery. We talked about the 2 transformer rectifiers. What's the only one left? Huh? The external, and we'll talk about that here in just a second. Now, just like the AC system, located on your power distribution panel, we have what's called a cross tie. Again, a cross tie is just like its AC counterpart. It will allow for either one of those transformer rectifiers to power up the entire DC system. Okay? The cross tie will allow for one power source to power up the entire DC system. And it'll do it how? Automatically, my favorite word. As long as that circuit breaker's in, it will automatically allow for a single DC system or single power source to power up both or the entire DC system. So there's your battery. Again, that's showing you the slab battery. Your transformer rectifier and external power located in the left electrical pod, but there's your external power source and where it connects on the left-hand side of the fuselage right in front. Between the electrical pod and the main fuselage, we'll show a close-up of it in just a little bit. Any questions so far? All right. Learning step activity 2. Describe the components, functions, and limitations of the AC power supply. We're going to start off with your main generators mounted to your aft transmission, which means the only time that the power from those generators are going to be available is when the rotor blades are turning. And notice that we don't turn on the main generators until our rotor RPM is set to 100%. Once it's set to 100%, then we'll turn those generators on, knowing that they're going to provide all the electrical power we need. Left-hand generator, known as the number 1 generator, is going to provide it for the number 1 electrical system. Right generator, number 2 generator, is going to provide it for the number 2 electrical system. Now, as we introduce the generators themselves, we're going to tell you that they are mounted to the aft transmission and they are cooled and lubricated via what? How are they cooled and lubricated? Oil. Okay, not the answer that I'm looking for. That's the shortcut answer. What's
The aft transmission main.
aft transmission main lubrication system? Keeping in mind, you can't just say oil. We got lots of oil running all over this aircraft. Okay? You can't just say main. Why? Because we have 6 main lubrication systems. And you can't just say aft transmission, because the aft transmission has how many lubrication systems? 2. Do both of them lubricate the generators? No. So the only correct answer is the aft transmission main lubrication system. That's what we're looking for, gentlemen. We don't make any beats about it. Okay? Now, what do we know about oil and electricity? Oil and electricity don't match, do they? They don't mix. As a matter of fact, they're about as incompatible as they come. So how in the world, on this aircraft, are we allowing our generators, our AC generators, to be cooled and lubricated using oil? And here's the misconception, okay? Where the actual electricity is created is sealed from oil intrusion. We're cooling in front of it, we're cooling behind it, and essentially cooling the whole generator. So where the actual electricity is being created is sealed from oil intrusion. But now, that doesn't stop the wires from running all over the place in there, right? So what else do you think they had to do to the wires? And this generator is a little bit heavy, and we are going to pass it around so you can look at it. But what you're going to find out as you look at this generator, that oil is going to be pumped into this area and this area, and that's how it's going to be cooling. And then what you're going to notice as you look at this generator, those wires have a coating protecting it from oil intrusion. Any questions about that? Now, as we look at how the oil gets to it, what you're going to find out is that oil is going to come in right there via the main lubrication system of the aft transmission. Yes, sir. Right there is where it comes in. Right there is where it comes in. And then what's going to happen is that oil is going to run down a chamber that's right here, or a channel that's right here. Okay? And then that oil is going to go down through that chamber, and it's going to go inside that shaft, where that shaft has a series of small little holes that, as the shaft is being turned, it's spraying oil into the different chambers. Gravity, in turn, is going to take it down to the bottom, where the scavenge pump is going to suck that oil back out and put it back into the lubrication system. Any questions about that? Okay.
That's for reduced electrical load.
Yes, sir. Yes, sir. So as we look at it, what it's going to look like is this. Oil is going to come in through that port, go through that chamber, and through the shaft, and it's going to be sprayed through its chambers. And then again, the scavenge is going to take it out. And you can see that in this center area, this is where the actual electricity is being created. And you'll notice that it's sealed from oil intrusion. Any questions about that? Now, we're going to introduce you to your generators, gentlemen. What you're going to find out is these generators are AC electrical systems, and they are also known as three-phase electrical systems. But as we introduce you to the three-phase electrical system, what you have to understand is these are Y-phase generators. And they're 120 degrees out from each other. And what you have is A phase, B phase, C phase. We tracking? Good. Why does that become important? Because there's a lot of people that misunderstand when we say that we have a 115/200 volts AC generators, which is the next thing that we're going to go into. It sounds like we're confused. What are they? Are they 115? Are they 120? What are, or excuse me, 200? What are they? And the answer is, here's my oscilloscope. And what we have in looking at an oscilloscope through basic electrical systems we normally have something like that, being a single phase, single AC electrical system. But in this aircraft we don't have a single AC electrical system, do we? We have a three-phase electrical system. So 120 degrees out from that, oops. I can never draw it like they do it. Okay. So 120 degrees out from that, we have something that looks like that. And then 120 degrees out from that, we have something that looks like that. Fair enough? So that's what we have. Now, if you want the mathematical formula, I have the mathematical formula too. Okay? But basically what you're going to find out through that mathematical formula, if I were to take my handy dandy marker, this is A phase, this is B phase, that's C phase. Everybody agree with that? If I took my handy dandy marker and I put my marker right there on A phase, would everybody agree with the poles being 120 out, I'd end up with something like that for B phase, and then something like that for C phase. Everybody agree with that? Resulting that if I took this power plus this power plus this power, which is very simplified, you're going to end up with 199.96 something something something. Hence 200. Does that make sense? Fair enough? Okay, now, here we go. In talking about that, 115/200 volts AC, what's the benefit from having a three-phase electrical system? Our house works just fine off of a single phase, right? So why would we want three phases?
It's a smoother power source.
What?
It's a smoother power source.
It's a smoother power source. Okay, what else?
Also, because of the way it's designed, they're able to make it produce more power and it'll be layered.
Okay, what else?
There's a lot of demand. There's a lot of demand put on the generator.
Okay, what else? Think about what we're using these generators to power up. We're asking them to power up computers of all kinds. Agreed? Wouldn't it be nice for those generators, or excuse me, for those computers, if we could maintain, as Carrie said, a smooth, but how about a constant, more reliable source of power? Would that make sense? When we think about alternating current, okay, and this will help you. What is happening with this alternating current? It starts off at 0, intensifies, intensifies, intensifies to the max capability, agree? And then it's going to actually start to de-intensify to where right here, what's happening? It's off, right? And then it starts to increase. Now, I can personally tell you I've never done this. But in helping you understand what's happening right there in that process, if you were to take a lamp and pull the shade off of it and turn the lamp on and just stare at it, what would you notice in that lamp? It pulsates or it flickers. Why? Because again, the intensity level's changing to the point where it's turning off. Off, 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 right? And we can go all the way down. Agreed? But what do we want for our computers? We don't want a power source that's fluctuating so much, right? But so by having three phases, our computers are going to run better. Now, what else? Our generators are 400 hertz. What is hertz? Frequency. Okay, translation, time. Right? Agreed? So what are we talking about? We throw that out like it's no big deal. It's 400 hertz. What are we talking about? We're talking 400 cycles per second. What is a cycle per second? Up, down, back up. We got 400 of those per second. Now, to help people understand that, here's the way I simplify that. Here in the continental United States, what do our houses operate off of?
60.
What is it?
60.
60 cycles per second. Okay, now, you notice I got some 50s in there. We're going to get to that. What do they work with in Europe and Asia? 50 cycles per second. So how does that affect anything? And the easiest way to understand it is if I take a clock that was made to operate here in the United States, and I take it to Europe, and let's go ahead and nip it in the bud. We're going to pretend like Europe and United States both operate off of 110 or 220. I don't care, okay? We're not going to get into that benefit, okay? I know the United States operates off of 115, 110, 115, and I know Europe operates off of 220, 240. I know that, okay? But we're going to pretend like we can take that clock and just plug it in over there. Fair enough? We're going to set that clock that was made to work where? In the States. Based off of what? 60 cycles per second, 60 hertz. And now it's in Europe, and we're going to plug it in where it's operating off of 50 cycles per second. 50 hertz. So what's that clock going to do? It's going to run slow. And likewise, because I believe in equal treatment, if we took a clock that was made to operate in Europe and we plug it in the United States, what's going to happen? It's going to run faster. Now, why is this important? Why do you care about this? Several things. First and foremost, what are we going to notice on this aircraft? How big are our gyros? Our gyros are in boxes, about like that, right? Why? Because what we do is we make those gyros at 400 cycles per second turn incredibly fast. By making them turn incredibly fast, what are we doing to those gyros? Desensitizing them, making them more efficient, more effective, more stable, all those good terms that we want to hear, right? The other thing about it is because they're turning at 400 cycles per second so incredibly fast, we can actually use smaller gyros to do that same thing. Any questions about that? Now, what you're going to find out tomorrow morning is we're going to talk about our fuel pumps. Okay, we've already talked about the engine-driven fuel pump, but tomorrow we're going to talk about our electrically operated fuel pumps inside our tanks. And you're going to find out that those fuel pumps are about that long and they're about that big in diameter. Incredibly small to pump the fuel that we need to pump. Again, why? Because at 400 cycles per second, they're turning incredibly fast. Okay, last thing, case in point. On the side of the aircraft, we have plugs that are just like this. Just like that. Giving you the misconception that we can plug anything into them that we want. Keeping in mind, we said our houses here in the United States were 110, 115, and that's 115, 200, okay? But what's going to hurt anything that we plug into it if it's not ready to accept it? The hertz, the cycles per second, okay? And all I can tell you is that when computers, laptops were first coming out, everybody remember how incredibly expensive they were? I had a young W2. Before I knew it, plugged his computer into it. And the only thing we could do was watch a puff of smoke come out. Okay? Why? Because he burnt out his power source. Now, luckily enough, it was brand new, so he was able to go ahead and take care of it. But you want to talk about seeing a grown man cry. And what he forgot about was not the voltage, but it was the hertz. It was the cycles per second that got him. Okay, so what can we plug into that? What type of things? Anything with a coil or an element can be plugged into it. Okay, why? Because basically all we're doing is heating something up. But if it has a timer, if it has a motor, if it has a compressor, if it has anything like that, you can't use those plugs. It'll burn it up. It's not set up for it. Any questions about that?
Is there
something in the flyaway kit, or why are those plugs on the aircraft?
They were originally there for special weapons. Okay, we later on started using them for some, like the logbooks that we have now, the computer logbooks, I do believe are able to plug into those, but they have a special power source that reduces it down so that it, or the hertz down so that it doesn't blow up the computers. But they were originally intended for special weapons. Some of the weapons that we carried on this aircraft required cooling or heating to maintain them. And that's why they were originally designed. Anything else? Even your track and balance equipment
Yeah, that's why I
uses
asked
a different, it uses a different plug on this aircraft. Any other questions? Okay. So any questions about the 115, 200, 400 hertz? Next is 40 kVA. kVA just stands for kilovolt amps. Instead of saying 40,000 volt amps, we just say 40 kVA. Fair enough? We don't need to make that one any more complicated than that. Now, here's something a lot of people don't realize. Inside of our generator is actually another generator. Okay? What you have inside this main generator back here is a PMG, which stands for Permanent Magnetic Generator. What's the difference between this generator and this generator? The difference is because these are permanent magnets inside of here, right here, and because those are permanent magnets, as long as this shaft is turning, a signal is going to be created. Now we're going to use that signal for a few things. First and foremost, we're going to use that signal for something we've already talked about, which was what? Rotor tach. Keeping in mind, how can it be used for a rotor tach? It's creating an electrical signal proportional to how fast what's turning. The aft transmission. So that's how we can use that signal for that. Any questions about that? Okay. Next, we're going to use that signal to create and power up our main generator. Why? What's the difference? These are not permanent magnets, which means we have to magnetize them. So how do we create that magnetic field? How do we magnetize it? We have to send power to it. So here's what's going to happen. Okay? And I'm going to draw this out, and we'll nip everything in the bud. Okay? This is my permanent magnetic generator. Okay, we'll go ahead and nip it in the bud. I know it looks like a bell, it's not a bell. Okay? I know it looks like an Arby's hat initially, but it's not an Arby's hat. This is my generator. Okay? Now, what's going to happen is this permanent magnetic generator signal is going to go to our GCU, which stands for Generator Control Unit. That's where it's going to go to. Okay? So what happens is that permanent magnetic generator signal and go into the GCU. Inside that GCU is a voltage regulator. We tracking? We good? Now what's going to happen is that voltage regulator is going to create what's known as your exciter field. And in creating that exciter field, that's what's going to create the output from the generator. Any questions about that? So that's where the AC generator is actually going to be controlled via that exciter or via that permanent magnetic generator. And what you're going to find out is that it's also going to be used to close a relay for the DC system too. So it's also part of the DC control. Any questions about that? Now, as we look at the APU generator, just so everybody has a warm fuzzy, that APU generator used to be one of two main generators on Charlie models and below. Now, why do I tell you that? Just so you know that it is quite capable of powering up everything we need to power up. It's still a three-phase generator system. It's still 115/200 volts AC. It's still 400 hertz. But where it changes is it is only 20 kilovolt amps, or 20 kVA. Now, let's go ahead and nip it in the bud. If you were to throw every switch in the cockpit, put as much of electrical demand on the system as you possibly could, the most this aircraft will be pulling is 15 kVA. So you've got plenty of power to provide for everything that you need. Now, the other big difference besides color is that this generator is air-cooled. Now, why do we highlight that? Where does the misconception come in? What class led to some confusion initially? Powertrain. And we looked at powertrain when we looked at the aft transmission main lubrication system. How many generators did it go to? Huh? It went to 3. What did we have to explain? Everybody thought it was generator number 1, generator number 2, and the APU generator. We said, no, it wasn't the APU generator because the APU generator is air-cooled. Okay? We had to explain that there was a third mounting pad for a third generator that would be cooled and lubricated off that system, should we ever need it. We have never needed it, and it's never been hooked up except for test activity, to the best of my knowledge. Not even the G or the E uses it. Any questions about that? Okay, now, we brought up one other difference, which was color. What does color have to do with anything? What's so special? Why are these main generators white? That doesn't sound like a very good color for something that's supposed to be camouflage.
The color changes when they get hot?
Yes, sir. This paint is a special paint that will change color if it's ever been exposed to heat. And therefore, that's what's special about this. And then the black generators, because they're from the predecessors, we just moved them into these. They were always black, they're still black. Now, the only other differences that you're going to really notice is that generator, the APU generator, has 6 wires connected to it. Why 6 wires? Why 6 wires, gentlemen? 3-phase electrical, right?
Yeah, but now you've got a number 1 and a number 2, where those are separate. This one, when it's operating, is running power to both systems.
But that's not why it has the extra wires. Keep in mind, because it's a 3-phase, what do we require? A phase has a positive and negative. B phase has a positive and negative. C phase has a positive and negative. But yet on this generator, you'll notice there's only 4 terminal wires that hook up to it. How do I get away with 4 here, but I have 6 up there? I still have an A phase, B phase, and C phase, right? I still have a requirement for an A positive, an A negative, a B positive negative, and a C positive negative. So what makes sense, gentlemen?
3 loose positives, 1 negative?
Yes, sir. 3 positives, 1 negative. It shares a common ground. It shares a common ground. Questions? All right. Any questions about anything we covered so far? Then we'll go ahead and we'll carry on. So we should be through page 6 now, and we're going to go to page 7 or page 527 of your handout. And what we're going to do now is we're going to talk about your power distribution panels. Key being, we call them PDPs for short, but literally what happens is whether the power source is AC or DC, it's going to come to those power distribution panels. From there, it's going to be distributed throughout the aircraft to all the systems and the components that require them. Whether it's radios, whether it's control boxes, whether it's other relays, because there's relays involved too. What a simple definition of a relay is nothing more than, in a lot of cases, a multi-switch. Meaning that it can either use one power source or another power source, or it may take a relay to actually connect something, additional equipment to that power source. Why? Because then we're reducing the demands power-wise until we need them. And that's where a lot of relays come in, and we'll talk about some relays. As we look at the power distribution panels, the first thing you notice is there are a series of circuit breakers. One of my favorite things to ask you is, what is the purpose of a circuit breaker? What is the purpose of a circuit breaker? Now, note the key word. I'm asking you the purpose. I'm not asking you how it works.
It's a safety device.
It's a safety device. I agree with that. Okay, for the purpose of what? Okay, for the purpose of what?
Over voltage.
Protect what now?
Over voltage.
Over voltage, okay. What did you say, sir?
Protecting the system that it's covering.
Okay, note what he said. He said protecting the system. Where does the misconception come in? The misconception is people think circuit breakers are to protect components. We don't care about the component. The component can go bad. It's not going to hurt us. But if we allow that component's failure to affect the rest of the electrical system, now we have a lot of problems. So the purpose of a circuit breaker is to protect the rest of the system. Does that make sense? Okay, and that's why we have circuit breakers on there, not to protect components. There's not a single component on this aircraft that is so important that we're going to lose the entire aircraft because of it. That's the nice thing about the Chinook. What's built into it? Redundancy after redundancy after redundancy. In this case, in electrical, how many generators would have to go bad before we have no chance for AC electrical system? All three. Yeah. Keeping in mind that if we have 714 engines, what's nice to know about aircraft equipped with 714? We can have a complete electrical failure, and because of the 30-volt DC alternator on that system, it will still operate those engines just fine. That's nice to know. That's neat to know. Okay. AC bus tie, gang bar. Again, nothing more than a method of allowing for a single power source. In this case, we're talking AC, to power up both the number 1 and number 2 AC systems simultaneously off of a single power source. Keeping in mind that that system is automatic. As long as that bus tie is on or up, that method or that process of, in case of a power source failing, the other power source picking up the load is automatic. So as pilots, the only thing you have to do is confirm, did the system work as advertised or didn't it? And up till now, that's been identified to you how? If you have a generator failure with a bus tie, then the result is going to be what? Just a single generator light. If you have a generator failure without a bus tie, up until now they pretty much have accepted that you know that there's more than one light that's going to illuminate, or there's several lights that are going to illuminate. They've accepted that for right now. But from here on out, they're going to expect you to know which lights and why. That's pretty fair, right? After electrical class. Relays for power distribution. Again, relays are nothing more than a switch type process. That's what it is. Okay? Current transformers are step down current. Why? Because some things operate off of less voltage, so the current transformers are inside of there. Lighting transformers for step down current. The lights require less power than everything else, so therefore they're in there. Instrument transformers. Now, why am I going to highlight this one? Keeping in mind that our oil pressure operated off of what? What did our engine oil pressure indicating system operate power-wise? You remember? 26 volts AC. There's where it's produced. Any questions about that? Now, of course, the left power distribution panel belongs to the number 1 electrical system. The right one belongs to the number 2 electrical system, and that follows the same thing that happens throughout the entire electrical system. Generator control units. Generator control units are going to provide for the following. Okay, first off, how many generator control units do we have? How many generator control units do we have? 3. Why 3? 1 for each one of the generators. 1 for each one of the generators. Now, what does this generator control unit do for us? It's going to provide for voltage regulation, as well as providing for fault detection, fault monitoring. Because you'll notice that if a generator fails, what interaction does it require from you except for confirming whether or not you had a failure with a bus tie or without a bus tie? Does it really require any action from you? No, because everything that needed to happen based on the type of fault that's detected, that generator control unit is going to provide for the appropriate measures. And we will talk about what those are here in just a second. For voltage regulation, we talked about the interaction between the permanent magnetic generator, the generator control unit, and inside the generator control unit we said was a voltage regulator, which is going to create the exciter field required to turn that main generator into producing electrical power. Any questions about that? Now, for fault monitoring, it's going to monitor for the following. Over voltage. That's kind of a no-brainer, right? Too much power getting out of there and getting through the systems is going to blow pieces and parts. Agreed? Don't want that to happen. That's bad. Under voltage. Not enough power is going to cause opponents not to operate the way they should, and therefore bad. Right? Now here's where it gets confusing. We did over voltage and then we did under voltage. Now we're going to do under frequency. What should have been the mindset? Or what is everybody going to be questioning right now? Why isn't it over frequency? Twofold process. One, all that's going to happen now is things are going to turn faster and be more efficient. So really, does frequency really hurt us in this case? Nope. But let's do one more favor. The most these generators can provide for, hertz-wise, if you look, is 420 hertz. Well within the acceptable parameters of all the components and systems. Fair enough? Good? So therefore, over frequency was not a concern. Which is why the next thing we went to was under frequency. But what's the problem with under frequency? Okay, not what we're looking for. What's the problem with under frequency? Why is that a major concern for us?
Well, there's two times where you can be concerned about it. One would be when you're on the ground,
Okay?
and the other time would be in the event that you have a rotor RPM drift.
Ah, that's what we're looking for, gentlemen. You can create or allow an under-frequency situation to occur. How? By allowing the rotor system to bleed down, which would be bad. Now, first off, let's talk about why is an under-frequency bad? What did we say was the benefit to the 400 hertz, the 400 cycles per second? Those gyros are turning incredibly fast. Well, now, if I wasn't providing for enough frequency, what would be the result? Those gyros would start to slow down, and as they start to slow down, what will start to happen? They'll start to wobble. And if they were allowed to wobble, what interaction do they have on this aircraft? AFCS, the Advanced Flight Control System. That would not be a good thing, would it? Okay? Now, what do we have that references that that's going to occur? We know that at 100% rotor RPM, equals 400 hertz. Good. Why? Because that's what the system's set up to do. So if this was slightly higher, what would this do? Go slightly higher. Agreed? Up to what? 420 max. Okay, now, here we go. What is the next reference that we have in our dash 10? What is our next concern area? Excuse me. But at that range for how long? 3 to 7. Meaning what? Meaning I can dip down into that range. And is it 85 or 87? It is 85. Okay. Let's make sure we get this right. Okay. When I get into that range, if I'm not in it for longer than 3 to 7 seconds, then nothing happens to my generators. But if I get into this rotor RPM for more than 3 to 7 seconds, then what's going to happen is it's going to fail or disconnect those generators from the electrical system. Why? Because of the interaction we were just talking about. It's bad for the systems, it's bad for the components, it's bad for the aircraft. So we're going to just disconnect it. Any questions about that? Now, here's the problem. When will it recover?
88.
88? Why? Based on what? Show me 88.
Based on rotor RPM.
What?
Based on rotor RPM.
Okay, but show me in the dash 10 where it says that. Show me in the dash 10 where it references that. We talk about when it'll fail, but what is the only reference we have for when it will recover? And it's actually a cheesy reference. I'm the first one to admit it. Would it be good to know when it's going to recover? Sure, it's going to, that is. Okay? So why don't they just say between 85 and 82% or above it will recover? What reference do we have as to when it will recover? %? Where did I pull that number from? What? Minimum rotor transient. Keeping in mind, gentlemen, at 91% rotor RPM, what's happening to my aircraft? I'm still descending. right? At 91% rotor RPM, I can't maintain flight. The aircraft's still coming out of the air. So why would 91% be a minimum for anything? There it is. It's for the recovering of the generators. Now, reality is, we'll go ahead and nip it in the bud, gentlemen. Wherever it probably disconnected it is probably the place that is going to be reconnected. But the 91 reference is the only thing we have based on your minimum rotor transient. Reality is, it doesn't give a darn about that rotor RPM. It doesn't care. What does it care about? It cares about that hertz. And the only reference you're going to find is in the Boeing book, and it's not in rotor RPM, it's in hertz. So what you have to do is translate where that is in rotor RPM, and that's where that 91 comes from. Any questions about that? Now, there used to be another reference in the Dash 10. They actually pulled it out. But the bottom line is anything below 82, what's the difference between happening, or what's going to happen here versus what's happening right here? What's going to be the difference? The difference is if you go below there, those generators are going to fail immediately. It does away with the 3 to 7 seconds. Does everybody understand that? Okay, where's it going to recover? Or what does it require me to do to recover it if I go below 82%? Ah, there's that nasty misconception, which is why they actually pulled it out of the Dash 10. Because when they saw the third one, the third reference, their mindset went from it recovering once we got above 91% rotor RPM to now I have to reset the generator. There's no such requirement. If I go down to 75% rotor RPM, the magic number is still 91. Okay? Meaning what? All you have to focus on is recovering your rotor RPM. The generators will recover themselves automatically. We good? Okay. Now, the next one is feeder fault. When we're talking about feeder fault, what are we talking about? You're going to notice off in parentheses, it's going to say open or short circuit. Open or short circuit. Keeping in mind, what are we talking about? Again, we've got to get the power from the power source, point A, to point B, being the component of the system. Agreed? What is an open circuit? An open circuit is a complete break. Caused by what? Caused by any numerous reasons. A lot of people complicate this by they trying to troubleshoot it. Reality is, you don't care. Okay? There's nothing you can do about that. But what do you need to know that the system's going to do for you? That's what we're going to talk about here in just a little bit. What is a short circuit? A short circuit is this wire still intact, but now what's happened is maybe that coating has come off, and now it's allowed to interact between the fuselage and that bare wire, causing what? Open or arcing and sparking. Now, even if it was a complete open circuit, the result is still going to be arcing and sparking, which is bad considering all the vapors and the fumes and the fact that this is a magnesium alloyed airframe. So in this case, what would I want my generator control units to do for me? What? Turn it off. I concur. I concur. But now what's the next question? Mr. Pilot, how does that accomplished?
PDP, GCU.
PDP, GCU. How is it accomplished? Circuit breakers pops out. Okay, I disagree on all those answers. So how does that occur? What have we learned so far that we could contribute to it? What have we learned so far that we could contribute to the process of turning off the generators? I like to make a standard joke. What do you think the GCU is going to do? Reach through its electrical pod and come up there and turn the switch off for you? Okay. Nope. It's sure not. You know where that came from? That came from one of your majors. He started that. The GCU is going to reach up there and turn it off. Okay.
He's gonna provide you with a light to tell you that something's wrong.
Okay, that is a fact, but that's not what we're looking for. The GCU is quite simply going to kill the exciter field. In killing the exciter field, it has now turned off the generator. But now, what do we know about electricity? It surges, it spikes, it's very, very flaky, right? So it could have been a momentarily thing, but now what is it going to have, or what requirements are going to be on me now to find out if the situation still exists?
Reset it.
Reset the generator. Reset the generator, which is going to in turn reset the GCU saying, hey, check it again. If the fault is still there, then guess what? It's going to give you a generator off caution capsule again, and it's going to kill the exciter field. Now, where do we have to go from this? How does it detect a feeder fault? And in order to do that, we're going to have to show you something else here in just a second. Okay? Now, I'm going to go ahead and come to this picture, but we're not done with the main generator GCUs yet. Why? Two things. One, the main generator GCU has what's called a byte indicator, built-in test equipment. It's going to consist of one of those magnetic latch indicators. It's going to trip black and white if it senses a fault inside of here. Now, there's one more thing that generator control unit does for you, and here's what I like to do to make you think. Okay, you ready? We're just cranking up the aircraft. We turn the APU on, and we turn the APU generator on. And how do you know that the APU generator is functioning?
Both rectifier lights go out.
Both rectifier lights go out. Now, up until now, that really didn't have a lot of meaning. But I'm hopefully going to get you excited about that. Because not only are you confirming that that generator is working when those rectifier lights go out, but what else are you confirming?
The bus stop.
That there's a bus tie. Now, a lot of people may not get excited about that, but I always did. Why? Because if it does it on the ground, if your AC bus tie system works on the ground, chances are your AC bus tie system is going to work in the air. So that's another little bit of a warm fuzzy. Okay, so now, here we go. I got my main engines online. I'm up to 100% rotor RPM. Generator 1 on, generator number 2 on. How do I know that those generators are working?
The lights go out.
What lights go out?
Generator 1 and 2.
Generator 1 and 2. Okay? The generator GCU is what turns those lights on and off. Now, why do I bring that up? Because the APU GCU does the exact same thing for the exact same reasons, with one exception.
No caution light.
No caution light. And it also does not have its own built-in test equipment. Why? Because back in those days, we didn't have them. Keeping in mind that this system transferred directly from the Charlie models and below directly into the Delta model. Any questions about that? Any questions about your control units? Alrighty, now, we're not done. because we talked about feeder fault, but now we need to talk about how is feeder fault detected. What you're going to find out, gentlemen, is right here is a component called a negative current transformer. Okay? I'm going to point them out. Right here is a negative current transformer. And quite simply, gentlemen, all it is in there is a coil of wire connected to a positive and negative. If I sent a wire through there with electricity, what is going to be induced at this point? What? Magnetism. Also.
Electrical field.
What?
Electrical field.
An electrical field. Magnetism, electrical field, heat. What else? It's going to induce current. It's going to induce current. And what's going to happen is inducing that current, it's going to send a signal, or it's going to send, and I'm just going to simplify it, it's going to send a signal to the GCU. Now that's easy to say. But what's induced, or what is understood by this process? That's the important thing. We knew, based on this process, that X amount of current came out of the generator. Agreed? Good? Now, inside the power distribution panel, which is ultimately where this power is going to be going to, we have what's known as positive current transformers. Now, reality is negative, positive, the result's the same. They work the same way. Basically, what they're trying to denote is one is measuring what's coming out. The positive is measuring what's coming to the power distribution panel. Fair enough? Now what's going to happen is through that, they're going to send a signal saying this is what got to the power distribution panel, PDP. X amount of current got here. The generator control units can figure out the difference between what came out and what got received, and based on a certain percentage, it knows that over traveling through lines, it's going to lose some, but it's going to be within acceptable power. As long as it's within acceptable power, it's good to go. It connects it to the system. It creates that exciter field. If there's a major difference between what came out and what got to the power distribution panel, it senses it as a feeder fault. And so it will not produce your exciter field. Everyone tracking? Any questions about that? And that's how a feeder fault is detected. That's the one for the number 1 generator. Guess what? The only difference is we're going to show you the number 2 PDP. We're showing you the same generator because that's the only one I have. Okay? The same process is occurring. Only now the positive current transformers are located in the right power distribution panel, the right PDP. But here's the catch-22. We can cheat and see that the APU generator negative current transformers, or excuse me, positive current transformers are located in that same power distribution panel. But where are the negative current transformers for the APU generator? Where are the negative current transformers for the APU generator? What? They're external from the generator, gentlemen. Where they are located is if you stand on the tarmac, if this is my ramp down and level, if you butt yourself up against directly underneath the APU, against the ramp, if you take half a step back, point directly up to your left, you're going to be by default pointing to them. They're often referred to as the donuts, but reality is those are your negative current transformers for the APU generator, which is providing for the same process. It's measuring what came out of the generator by inducing current. The positive current transformers are inside the PDP, measuring what got there, and the only difference is they're going to their control unit, which is the APU generator control unit, located where? In the right electrical pod. Keeping in mind, we know that the APU generator is the most confusing of the systems. Why? Because everything for it is in the right side of the aircraft, the right electrical pod, the right power distribution panel. But the result is going to be where? Number one PDP. Where's that, and why is that going to become important to understand as pilots? That sounds mechanical to me again. That sounds something like the flight engineers should know. Why is it important to you? If I have a dual generator failure and I can't get either one of those generators, by cranking up the APU, the only thing I'm going to power up initially is what? Number one PDP. It's using the automatic bus tie system to now power up the number two PDP. So if there is a problem with the automatic bus tie system, the only thing that you know that you will have for sure is the number one electrical system. Does that make sense? And that's the only reason why that knowledge is important. Any questions about that? Now, the contactor relays. The contactor relays. On the bottom of page 9, keeping in mind, when we talk about the contactor relays, sounds complicated, but reality is it's going to provide for three things. What's it going to provide for? One, it's going to ensure that only one power source is connected to a bus at a time. I'll say that again. It's going to ensure that a single power source is connected to a bus at a time. Why? Because if I allowed more than one electrical source to get to one power or one bus, what's going to be the result? Over voltage, and it's going to fry the system. Agreed? So that would be a bad thing. Next, it is going to provide for the prevention of reverse current. It's going to provide for the prevention of reverse current. Why is reverse current a concern?
There are a couple of pumps and those kind of things working on it.
Say that again?
There are a couple of pumps and spinning things, vertical gyro that's working off it. So
Okay.
Turn the other way around.
Not exactly what I'm looking at. Okay, why is there a possibility, why is there a concern for reverse current, gentlemen? Think about it. We already know that a single power source can power up both systems, right? On a system that was made to have what? One generator is going to provide a source of power from the number one system. Number two generator is going to provide a source of power for the number two system. But in the case of a failure, this generator can pick up the load of both systems. But what do I know about electricity? What do I know about electricity? What do I know about anything?
If you reverse the current, don't you then in fact change the positive and negative?
Okay, but now what I'm looking for, that is a fact.
Working generator might want to power up the other generator.
Bingo! Why? It's a term that we are used to hearing. What? The electricity wants to follow the path of least resistance. Electricity wants to follow the path of least resistance. And think about it. What does it? let's see. If I make this decision, it's going to cause me a lot of work. If I make this decision, I can skate by and just do what I need to do. Which path am I going to go? I'm going to go down this one. Why? It's easier. But now, what happens if I were to allow power to go backwards through this generator? If I sent power backwards through a generator, what happens to it?
Sparks.
Not necessarily. We do have sparks, but it's caused by what? What would happen if I sent power backwards through a generator? What does it become, gentlemen?
Motor.
A motor. So now we're going to take something that was meant to be driven, and it's going to want to drive, and all that arcing and sparking and bad things is going to happen from those gears fighting each other. But what you have is a shearable shaft. As an ultimate, if that does occur, it will shear the shaft first.
They don't put a spline adapter on to shear instead of shearing the shaft.
No, it's a shearable shaft.
Yeah.
Yep. And it always has been. Any questions about that? Okay, and last but not least, what is the third and final function? The third and final function is we said that if the generator control unit senses an over voltage, under voltage, under frequency, that it did what to those generators? Did it turn it off? Did we say it turns it off? No, we didn't say it turns it off. We said that it does what? It disconnects it. It disconnects it.
Now, is that the term you want to use? Because in the handout it says the GCU will turn it off.
Yeah, because you got to understand the difference. Okay? What happens in the case of an over voltage, under frequency, is it just disconnects that generator. And we're going to talk about how that process occurs here in just a second. Okay? So I'll tell you what. We'll hold that off until we explain it better, and then you help me decide. Fair enough? Okay, so here we go. How does it work? What you're going to notice is we actually have a control unit, a contactor relay for each and every power source that we have. So how many contactor relays do we have? 4. I agree with Bus. We're not even going to play games. 4. That is a fact. 1 for the number 1 generator, 1 for the number 2 generator, 1 for the APU generator, 1 for the external power source. Fair enough? Now, here's what I like to do with these. Now, before I do that, what I'm going to tell you is these are yours to mark up as you see fit. Okay? And I am going to make a recommendation to you. If you're not going to keep it, then don't mark it up, because I can give it out to somebody else. If you mark them up, then most people don't want them. And unfortunately, then I have to throw them away. But if you know you're going to keep them, then you mark them up. And here's what I'm going to recommend. Okay? What you're going to notice, and I'm going to use Jeff's here, here are all my contactors. All a nice little pretty row. Good? Everybody see that? Those are all my contactors. And here's what we're going to do, gentlemen. We're going to start off with the same power source that you start off with, which is which one?
APU generator.
Which is the APU generator. So everybody locate your APU generator. And what you're going to notice, if you followed that to your right, you're going to see that it goes to the generator contactor, the APU generator contactor. But there's a missing portion of that you need to understand. Or there's a missing relationship to that you need to understand. And here's what I'm going to recommend. Right by the control unit, right by the contactor, and we're just going to do this one time. Here's the APU generator. Everybody agree? From there, it goes to the APU generator contactor. Everybody agree? Now, here's the relationship that you need to know. I recommend you draw another box. And what are we going to put in that box? APU generator control unit. Why? Something has to tell this APU generator and contactor whether or not power is being provided. Agreed? So that APU generator generator control unit, based on receiving power saying, yep, my APU generator is powered up, is now going to cause that contactor to do this. Here's what's going on inside that contactor. You ready? That contactor is just going to go like this. And now it's going to allow its power to continue on its merry way. Everyone tracking that? Now, why am I doing this? Because if you don't know, on a schematic, this is the symbol for a switch. A multi-switch, actually. That's what that is. And that's all that's inside of there. So that's going to contact saying, now, power, you can go from point A to point B. Good? Now, we said that it prevents reverse current. How does it prevent reverse current? Looking at this. In order for this power to jump and go to here, there would have to be a hell of a lot of power created to allow that process to occur. Agreed? So that's how it prevents reverse current. Any questions about that? Okay, now, you'll notice from there, it goes down to the number 1 generator contactor. And again, what's missing from that process? The GCU, the number 1 generator control unit. Number 1 generator control unit is going to say what? Hey, my power source at this point is not cranked up. Everybody agree? So what's going to be allowed to happen is it's going to send its path down its merry way. We tracking? We good? Now, where's its merry way? To the number 1 power distribution panel. We tracking? Now, if you look at the very top of that, you're going to notice that that power comes back out through the automatic bus tie system. That's what that symbol is with the 3 arrows signifying your A, B, C phase. Everybody see where we're at? Okay. We followed up the power distribution panel to the top through the automatic bus tie system. Okay, and it's labeled number 1 gang bar. Everybody see that? Okay, now, external power contactor. What do we have going on again? Here we go. Now, what's going to happen? What do we need to draw in this process? External power control unit, right? External power control unit is going to say, hey, my power is not available, and it's going to allow that switch to connect. We good? Now that power is going to go up to where? The number 2 generator contactor. So what are we going to have to draw there?
GCU.
The number 2 GCU. Now what's going to happen? Here we go again. You ready? Number 2 generator control unit is going to say, hey, my generator is not powered up. Go through your merry way, and now it's going to go to the number 2 PDP. So both the number 1 AC electrical system, number 2 AC electrical system is now being powered up from the APU generator through your automatic bus tie system, your gang bar. Does everybody see that now? Okay, good. Now, Where's the rest of the equation come in? You ready? Now we got the generators online. We're up to 100% rotor RPM. And we're going to flip generator switch number 1 on. What was it originally powered up off of? The APU generator. So now what's going to happen is what? That relay is now going to go like this. And it's going to switch. Turn on the number 2 generator, and the same thing's going to be allowed to happen. Instead of using the APU generator through the automatic bus tie system, it's now going to use its associated generator. We good? Okay, so now, here we go. The generator control unit says, hey, number 2 generator's not working right. Either an over voltage, under frequency is irrelevant. What's going to be allowed to happen? Boom. Good? Now, has the generator been turned off at this point? No, it's just disconnected from the bus. Right? Now, what you're going to notice in the case of a dual generator failure, it's going to tell you, 1, put both gang bars down. Why am I putting both gang bars down? Essentially, what am I doing to the system? What am I telling the system? I'm separating them. Number 1, power up number 1. Number 2, power up number 2. I don't want to worry about a AC bus tie right now. All I want to do is recover one of my electrical systems. Agreed? Now, how is that allowed to occur? Because the automatic bus tie system is no longer in the picture, if the problem was in the number 2 system, then the chances are I may be able to get the number 1 generator back online. If the problem was in the number 2, in the number 1 system, I may be able to get the number 2 generator online. And then keep in mind, because electricity is flaky, because it's unpredictable, we don't know if it was just a power spike or surge or something like that. So what's it going to tell me to do? Go ahead and put the gang bars back up. In the hopes of what? That now that one recovered power source that I have recovered can still power up both systems. But guess what? If it pops the system again and tells me I can't do it, then I know, okay, I'm going to recrank my number 2 generator, and I'm just going to leave the cross tie the way it is, the AC bus tie the way it is, and therefore I'm going to have one electrical system, and now I'm in a situation known as what? What situation am I going to be in? A generator failure without a bus tie. So I now know my emergency procedure is what? Land as soon as possible. Everybody understand that? Questions? Okay. Now, here we go. You'll notice that I stayed on this picture the whole time. What we're going to do is we're going to go through the same process, only this time we're going to look at the contactors. So the first contactor we're going to locate is the APU generator, which by now we know is located where? Where's the APU generator contactor? Where would we think it is?
Number 2 P.
It's in the number 2, but we'd think it was in the number 1, because why? We know that it powers up the number 1 PDP, and this is why the APU generator gets a little confusing. Okay? But it is in the number 2 PDP. You're 100% correct. So now what's going to happen is from this contactor, we said that power is going to go where? To the number 1 generator contactor. From the number 1 generator contactor, we said that it's going to go where? To the external. Through what system? The AC bus tie system. From there, it's going to go where? To that number 2 generator contactor to power up the number 2 PDP. So you see what it did? It went from here to here, up to here, over to here before it was finished. When I turned on both generators, now what's going to happen is what? These contactor relays are going to switch allowing its generator to power up its PDP, and the number 2 system is going to do the same thing. So now, at this point, what is my automatic bus tie system doing for me? What?
Opens, or at least.
At this point, what is my automatic bus tie system doing for me? The answer is zip, zilch, nada, and nothing. Why? Because each one of the electrical systems, each one of the generators are powering up its own PDP right now. So the next time that it would be factored in is in case of what? A generator failure. So what's the system doing? If both generators are working, it's sitting there in standby. Standby for what? In case of one of those generators failing. Questions? Okay, let's go ahead and get started. Any questions about the contactor or relays? Does that help make sense of it? And the neat thing about it is what do you do to control that system? The only thing you can do is make sure that the AC bus tie is up and on. Okay, now, the only other question is, you'll notice that AC bus tie is pretty big and thick. Why? Why is it so thick? What do we know? We know that those generators are a 3-phase electrical system. What would happen if I were to be able to pull 1-phase, 2-phase, 3-phase, or A phase, B phase, C phase?
Is that why there's 333?
Exactly. What you're doing is you're just controlling all 3 simultaneously. That's the only thing that's happening. Does that make sense now? Which is why it's denoted in here as 3. We know it's only a bar, but reality is there's actually 3 circuit breakers that are actually being taken care of simultaneously. Overhead control switches. Now, this is one of those panels that you have to be familiar with going into nights. Meaning what? Meaning without looking, you have to be able to, 1, identify the panel itself, 2, the location of the switches, and 3, the position of the switches as you go into nights, which makes sense, right? When you first climb into an aircraft, it's dark, and if you don't know where those switches are, what's happening, it's kind of hard to do what we need to do. And in order to help you do that, and helping you get familiar with this panel, I like to just put it in the order that we're going to operate it in. And what's the first part of the equation? The first part of the equation is being able to locate the panel. Agreed? It's in the overhead panel, bottom left-hand corner. So now all I have to do is find the overhead panel, bottom left-hand corner. As soon as I find the corner, I know the next place I'm coming is that electrical panel. Agreed? If I find the corner, the first switch I'm probably going to realistically contact is your number 1 generator. But I don't want the number 1 generator yet. What do I want? The battery, directly above that. And you got a 2-position switch. Off, on, keeping in mind what is the rule for all switchology in just about every aircraft that you're going to be associated with. On is forward, down and forward is on. So that's the position. So it's a 2-position switch. I'm going to move it down to the on position. Now what's the next portion of this equation? I'm going to crank the APU, right? So I go straight across, my APU start switch, keeping in mind that that's a 3-position switch. What am I going to do? It's in the off position. All I'm going to think in my head is what process? The start process, right? So it's going to go run for 3 to 5 seconds, start for 2 seconds, release it. It's sprung loaded back to the run position. Cool? Now I'm going to be looking for what to happen. First light I'm looking for is what? APU on caution light, and then I'm looking for the utility hydraulic caution capsule to go out within 30 seconds. And then straight down, I'm going to come to the APU generator switch. Keeping in mind that the switch itself gives you the misconception that it is a 3-position switch. It's actually only a 2-position switch. The 3rd position does not actually do anything for the APU generator. So what you have is you have a test position, off reset, on. It's going to be in the off reset position. The only thing we have to do is move it down to the on position. When we move it down to the on position, now what am we looking for? You're looking for the left and right transformer rectifiers, or the number 1 and number 2 rectifier lights to go out. That confirms for me what? That the APU generator is working and that an AC bus tie exists. Those are the 2 things that are being confirmed by that process. Now here's the neat thing. If I were to go from that switch to the next generator, I would actually want to go to the number 1, but actually in between the APU generator and the number 1 generator is the number 2 generator. Agreed? But watch this. What do I do from here? Well, I'm going to go through all sorts of series of checks, ain't I? So my hand's going to come back down and I'm going to start going through those checks. Agreed? So the next time I'm going to be reaching for that panel is both engines are online, we're at 100% rotor RPM, and now I'm ready to turn the number 1 and number 2 generator on. So all I have to do is start back at the beginning again and start with locating the panel. I find my corner, the first one I come to is my generator, number 1 generator. Number 1 generator on, looking for the number 1 generator off caution capsule to go out. Number 2 generator on, and I followed my exact order, and I was able to do all my switchology. Agreed? So what's the only thing that we need to talk about? We need to talk about the reset position. The test position. Because it's off reset. What is going to be the tendency in the case of an electrical failure, in the case of doing the procedure, what is going to be the temptation?
Go to test.
Go to test. And I promise you, gentlemen, most of you will do it. And I promise you, the IP is going to know that you're going to do it. So don't even try to BS them. You can't. But let me tell you how they're identifying it. Is that fair enough? And that'll help you understand what the process is. Okay? When we troubleshoot the generators, in the case of a dual generator failure, it's going to tell me to go to the off reset position. I'm going to be tempted to go to the test position. Now, my my main generator off caution capsule was already on. Agreed? If I go anywhere other than the off reset position, I go to the test position. What's going to happen in the test position is it's going to test the system for an over voltage, under frequency, and feeder fault. If it senses any of those, how do you think it's going to tell me whether or not it sensed it or not? What's the only thing you have? Is the generator off caution capsule. So if it doesn't sense any one of those problems, what's going to happen is that light is now going to come or go back out. Okay, the generator off caution capsule came on. Why? Because the generator was off. I went through the off reset, it turned it off. Go to the test position, that light's going to go back out. If it doesn't sense an over voltage, under frequency feeder fault, then it's going to turn the light back out. But now, in order to get back to the on position, what do I have to do? I have to go back through the off reset. So what's it going to do to the light? It comes back on. And then I go back to the on position, what's going to happen?
Should go off.
The light goes back out, should go off. So that's how they'll tell that you'll mess it up. And remember, in the aircraft, there's nothing wrong with the aircraft. So when you're doing this process, that's what it looks like. Reality is, if you were to do it in the real thing, under the real emergency conditions, chances are, 1, they're not going to notice. 2, they're not going to care. And 3, it's not going to be that big of a deal. It doesn't hurt anything, which is the big thing. Okay? Why is it a big deal then during the training process? Because they want you to understand that you should just go to the off reset position. You shouldn't go all the way back to the test. There's no requirement for you to test the system. Reality is, as maintenance test pilots, they don't test the system anymore. Why? What do we have in the process now? We have generator control units that are doing what for you?
Finding a bit.
They're monitoring for overvoltage, undervoltage, underfrequency, feed, or fault. So reality is there's no requirement to test it. Any questions about that? Any questions about the overhead panel? Okay. And all this next picture is going to do. Okay. I forgot I took it out. Okay. Any questions about your overhead controls? Now, looking at the external power source, keeping in mind that when we talk about the external power source is an external power source is an external power source. It's going to provide for both AC and DC. The power source itself is the same one. Fair enough? The access panel for both AC and DC is located in the same spot. It's on the left side of the fuselage, in between the left electrical pod and the main fuselage. There's an access panel in there. In there, you have your AC system, you have your DC system. Now you'll notice I got a big pole, little pole, big pole, little pole, big pole, big pole. Why?
Small little ones are the grounds, negative ground.
Okay, so we got positive and negative, but why big pole, little pole, big pole, little pole, big pole, big pole?
So you don't turn it around.
So you can't hook it on backwards because it is phase sensitive. That's the only reason. It doesn't change how the system operates. It doesn't change anything else. It just makes the system idiot-proof for hooking the electrical connection. And why? Because the aircraft is phase sensitive. So why don't we make a big deal about phasing? Because the system is idiot-proof. As long as the wires on the generators are hooked up right, the phasing is going to be right by default. Does that make sense? Now, if we hook it up wrong, it's still going to be during maintenance. And reality is, the first time we crank it up, the generator control units, because they are monitoring for phase, will say that it's not connected, and then we'll have to troubleshoot it, and we'll find out that they hooked the wires wrong. But that's long before you even come out to try to fly the aircraft. Any questions about that? Now, inside the left electrical pod is your external power control unit. Again, because our control units are auxiliary ground power units, aviation ground power units, AGPUs, all the same things, all doing the same job. Now, because they're so multifaceted today, they have a lot of different power settings, they have a lot of different voltages, they have a lot of different capabilities. They can power up a lot of different pieces of equipment. So therefore, we have to protect the aircraft. And what we have is the external power control unit that's going to monitor for everything, making sure what? That we're hooking up the right capabilities for the right process. Why do I say process? This is the same one for AC and DC. It's the same one for AC and DC. In that same left electrical pod, you have your reset switch does the same purpose. If it senses a wrong setting, it disconnects it or does not allow it to connect to the aircraft. If it senses a fault, it will disconnect it from the aircraft automatically. In which case, the reset button tells the external power control unit, we fixed the problem, go check it out. Good? So the next question is, how is the fault detected? Or excuse me, how is it identified to us? And here's the question. In a lot of aircrafts, the switch that actually controls the external power control light up in the cockpit is normally associated with what process in most aircraft? Does anybody remember?
It's just plugged in.
What?
It's just plugged in.
Actually, no, that wasn't the process that it started off with.
It was actually power applied.
No. There used to be a micro switch connected to the door itself. So if the door was open, it would turn on the light in the cockpit. Okay? That's where it started. And then later on it became if it's plugged in. And now in this aircraft, it's important that you understand that the only time that it will light this light is if the aircraft is actually using that power source to provide electricity. I'll say that again. Okay? The only time it will light that light is if the aircraft is using that power source. Why does that become important? Because on page 11, you got a very, very embarrassing note. Unfortunately, that comes directly out of your dash 10. And that note's going to read the following. When external power is used, a visual check shall be made by the crew to ensure that the external power unit has been disconnected from the helicopter before taxiing. If you haven't put 2 plus 2 together, we have attempted to tow that auxiliary ground power unit along with the aircraft, or we've attempted to make it a sling load. Not a very good thing. Why? What is the mentality? When is the external power control unit, or excuse me, external power unit going to be used? During what process did we say? Maintenance. What is the mentality of our maintenance personnel, our maintenance pilots? Hurry, 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 hurry. Let's get the job done. Let's get the aircraft back up. Agreed? So that's why we tend to make more mistakes there. And that's where that comes from. So now, the next thing we have to understand is why is that a possibility? And that's based on the AC priority. The priority is going to be your main generators first. APU generator second. And then external power source. So even if I had the external power source connected and it was using it, as soon as I cranked up the APU and the APU generator, that external power light went out. And that's why that problem is allowed to occur, of accidentally trying to make it a sling load or accidentally trying to tow it along. Any questions about that? All right. Now we're going to look at the DC system, which again is going to consist of the overhead panel, 2 transformer rectifiers located in the left and right electrical pod, a battery located in the left pod. If we're talking the NiCad battery only, we got a battery charger. Battery relay, external power switch, keeping in mind the external power switch is the same one that we just talked about before. And then of course, power distribution panels. The one thing that I failed to mention when we talked about the power distribution panels, to help you learn and identify circuit breakers easier, the top of the panels are your DC control. The bottom of the panel is your AC. That's the breakdown. They're labeled row 1 through 22. In the top half, you got A, B, C, D, E. And on the bottom, you have A, B, C, D. That's the breakdown, okay, in learning that panel. But we have an actual line that denotes everything above that line is DC. Everything below that line is AC. Any questions about that? Now what you'll notice in a lot of those circuit breakers, you have a DC control that will marry up with an AC circuit breaker down at the bottom. Why? Again, everything on this aircraft is DC controlled, AC operated. So there's a lot of things that have both a DC circuit breaker as well as an AC circuit breaker. So you have to remember to check both circuit breakers. Any questions about that? And then you do have some things that are unique between the number 1 and number 2 side. And we'll talk about one of those here in just a second. First thing we're going to talk about is our battery. In talking about our battery, the first thing we're going to tell you is that these batteries are 24-volt DC batteries. I'll say that again. These batteries are 24-volt DC batteries. That sounds like a no-brainer. So where does the confusion come in, gentlemen? Why am I emphasizing that it is a 24-volt battery?
Because of what our other systems operate off of.
Okay, what is the primary?
So 28.
Normal is 28. So what happens with the 4 volts DC? What happens to it if the battery's 24? Reality is we do not use the battery to back up a lot of things. Okay? As a matter of fact, the primary use of our battery is to crank our APU. That is the primary job of that battery. Because once the APU is cranked up, the next thing we're going to crank up is the APU generator, which is going to provide for both number 1 and number 2 DC systems. We tracking? We good? So our primary use of our battery is to get our APU online. Now, the 2 batteries we're going to talk about, again, is our NiCad battery located on the right side of that picture, and our slab battery. Now, as we look at the batteries, there's your slab battery, there's your NiCad battery. Now you'll notice another difference too, and I'll go backwards. Your NiCad battery not only has your primary connection, positive and negative, but it also has this little connection down here. If I were to go backwards and show you the slab battery, you know that, notice that little cannon plug goes away. Any questions about that? Now, the battery is going to provide for 3 of your DC bus. What you're going to find out, gentlemen, you ready? You have 5 DC bus. You have 5 DC bus. And what we're going to do is we're actually going to use this to identify them. So what I'm going to ask you to do is find your battery, which should be located slightly to the right in the middle of your diagram. Everybody find it? Now, from the battery, if you go straight down, you notice that it's going to go to the hot battery bus. And what you're going to notice is on that hot battery bus, you have 2 wonderful circuit breakers. If you located the battery and you came straight down, you should have located the hot battery bus. On there, there's going to be 2 circuit breakers. One is going to be marked your hydraulic level indication, meaning what? Meaning when I go to the maintenance panel and I push my hydraulic level indicator, it's drawing power off that hot battery bus. Any questions about that? Then the next one is going to be your APU control. Actually, APU emergency control. For what process? For starting the APU. What this does is allows you to start the APU without turning on the battery. I'll say that again. What that allows for is you to crank the APU without turning on the battery. Any questions about that? Why? Because you'll notice that the normal APU start is on what we refer to as the essential DC bus. But you'll notice, if you look at the essential DC bus, there's a whole bunch of other things powered up at that same time, right? Well, by not turning on that battery switch, there's only those 2 processes occurring, so therefore every little bit of power that that battery has left is now going to be directed towards starting the APU. And that's why the process works the way it does. Any questions about that? Now, here we go. You ready, gentlemen? Locate your battery again. Come to your right, and you're going to notice that it goes to the battery relay. Guess what that relay is? That's that big hunkin' relay directly above the battery. So here's my battery. Whether it's a slab battery or a NiCad battery, it doesn't matter. There's that relay. And again, all this relay is a multi-switch. That's all it is. Allowing for what? Allowing for several pieces and parts through that relay to be connected to this battery. We tracking? Now, you're going to notice that it's, from there it's going to go down to the switch battery bus relay. Fair enough? I'm not going to define relay anymore. I think we've got relay. Agreed? And then it's going to go down to the switch battery bus. And what you're going to notice is there are 5 things on that switch battery bus. First one is your control centering device release, meaning what? Gentlemen, all you have to do with that battery plugged in is push that control centering device release button, whether it's the one on the cyclic for your pitch, roll, and yaw axis, or the one on the thrust control is irrelevant. What you're doing is releasing the magnetic brakes. Even though you don't have any hydraulics applied, even though you can't move them, they will still release based off of that bus. So what will happen is if you push it, what you will hear in the flight control closet is a series of click, click, clicks. Why? Because those mag brakes are actually releasing. By how? By applying power. And then when you release it, the power goes away, locking them back up. And that's what your process you're hearing. Good?
Why is that on the battery bus?
Why it's on the switch battery bus? That way, if we have a transformer rectifier failure, we still have the ability to release those mag brakes. In case of what process? The transformer rectifiers can go bad, but now I can use I can use the battery as a source of power to release those mag brakes. So as long as
Necessary use of your battery power, it seems to me.
well, if that's all you have to get the aircraft to the ground,
Well, you fly it.
no, you can't. Well, yes, you can. I'm sorry. Yes, you can. But they wanted to make sure that those brakes could be released. In particular, which one is important? Thrust. So, but it was applied to them all. Good point. Yeah. Okay. So next, we got ramp and cabin lighting. Good? Next is one that you are going to forget all the time. Why? Because I do. Why? Because we don't use it. Directly behind the pilot's head is a light switch. And that light switch is going to control a light on bulkhead 95 pointing aft towards the forward transmission oil level indication. That's all that light's for. Good? Next is your refueling station. Meaning what? Meaning when I turn my overhead switch on my overhead fuel panel, when I turn the refueling station on, it's drawing power off of that bus. And we'll talk more about that tomorrow. And then last but not least, your emergency exit lights. But keeping in mind, if you do not turn off your emergency exit lights properly, this is where you will kill off your battery. Keeping in mind that it is a dual indemnity process, meaning what? Meaning if you don't turn it off, you're going to damage something. You're either going to draw power off the aircraft battery, possibly killing it overnight, or you're going to kill the internal batteries of your emergency exit lights.
I mean, if you don't place it in the disarm position instead of the off position?
Exactly. Meaning if you don't go up to the disarm position and then back to the test position, keeping in mind that's a 3-position switch, but off is not one of the positions. You go from the arm all the way forward to the disarm all the way back. And what that does is it pulls that system off of that inertia switch in the back of the aircraft for the process of turning those emergency exit lights on in a 3 to 4 CG crash scenario. Good? If I leave it there, the process that people forget about is that those lights are meant to come on in the case of a complete electrical failure too. But now, what power source is it going to be using? Inside those emergency exit lights is a battery. So if I disconnect that battery to protect the battery from going dead, the aircraft battery from going dead, what's that tell to the system? simulates an electrical failure. So now what's going to happen are those lights are going to come on. And when are they going to find out? They're going to find out after they disconnect that battery, which is why crew chiefs and flight engineers get a little frustrated. Because now they have to go unlock the door, climb back in, after they plug the system back up, crank the APU, turn it back off properly, and then start the process all over again. Okay, so you have to go to the disarm and into the test position. That's the proper way to turn it off. Now, here's my question. When is the hot battery bus available? When is the hot battery bus available?
When the battery charged.
What?
When the battery charged.
Okay, now what I'm looking for.
Yeah, good night.
As long as the battery is connected, the hot battery bus is available. We tracking? So what's the next question? When is the switch battery bus available?
Battery relay is on.
Give me a better. What? When the battery switch is on. Wrong.
That can't be true.
It's connected to the outside.
As long as that battery is connected. So then why do we refer to it as a switch battery bus if it has nothing to do with the overhead switch? Just keep that thought process going just for a moment. Okay? We're going to go to the essential DC bus. Now, gentlemen, I'm not going to impress you off this essential DC bus. Why? Because there's too many things at this point that are going to start powering up. There's so many things that are going to be powered up. You're going to notice that essential DC bus is providing power to both the number 1 and number 2 PDP. So what's the difference between the number 1 and number 2 PDP? The essential DC bus is going to be powering up the number 1 and number 2 PDP, but it's still only going to be processing what is connected to the essential DC bus. So now the next question is when is the essential DC bus available? When is the essential DC bus available? What?
When the battery switch on.
When you turn the battery switch on. Okay, so we're tracking now? So now we have our hot battery bus, our switch battery bus, and our essential DC bus. And they are all using what power source at this point? The battery. Does everybody understand that? We good? Now, in order to get the number 1 or number 2 DC bus, and I will accept 2 answers, what do we need?
AC power.
Very good. That's the one everybody forgets. What's the one they automatically go to? When the transformer rectifiers are available. That is a fact. That's 100% correct. But in order to have the transformer rectifiers, what do I need to have? A source of AC power. It doesn't matter what source, I just need one. Why? Because any one of the AC power sources will power up the 2 transformer rectifiers. Good? Now, here's where the magic comes in, gentlemen. Remember, I asked you a question. Why is the switch battery bus called the switch battery bus if it has nothing to do with the overhead switch? What will happen at this point
Because
is
it
it...
automatically switches when the rectifier is coming on?
Yes, sir. It will switch from using the battery as a source of power to the transformer rectifiers as a source of power. And so will the essential DC bus. So at this point, once we have a transformer rectifier, 4 out of the 5 DC systems that we just talked about are now powered up off of the transformer rectifiers. Does that make sense? The only one that does not switch is which one?
Number 2 DC bus.
No. The what? The hot battery bus is the only one of the 5 DC systems that does not switch power sources. It is and always will be the battery. Where the switch battery bus can use both the battery and the transformer rectifier, which you will notice anything that refers to the switch battery bus or the essential DC bus is designated what way? It's always designated like this. 24/28, denoting what? That it can either use the battery or the transformer rectifier as a source of power. Yes, sir.
What I don't get is from this piece of paper, the number 2 DC bus looks like it doesn't need the battery to.
You're right, it doesn't, sir. Transformer rectifier, it only uses the number 2 DC system will only use the rectifier. But you'll notice the primary means to power up the the switch battery bus and the essential bus comes off the number 1 transformer rectifier. Primary. But it can also use the crossover or cross tie, which will result in the same thing.
That's what
Well, there's another reason why you land as soon as possible. And we'll talk about that here in just a second. That's just part of the reason. We tracking, keep in mind the number 1 and number 2 DC systems are now powered up off of their associated transformer rectifier. But just like we talked about before, in the case of one of the rectifiers failing, the other rectifier will pick up the load of the entire DC system. And I was very careful not to specify 1 and 2. Why? Because there's actually 5 DC systems. A hot battery bus, the switch battery bus, the essential DC bus, the number 1 and number 2 DC bus. In the case of a transformer rectifier being powered up, the only one that does not switch power sources is the hot battery bus. Everybody tracking?
So even though you have, for the essential buses, the PDPs for the number 1 and number 2, it's still only considered one bus?
Yes, sir. Based on the time that it is powered up. Anything else? What was your question, sir?
Yeah, about the switch battery bus, I don't get it. That it can be powered by the transformer rectifiers.
Okay. You've got the essential bus relay right here, and then you got the switch relay.
Yeah.
That's going to come up through here, through here, and now power up
But
this system.
this small part doesn't mean battery only. Because that's what it says in the.
I know.
But it's still,
I know. We're gonna fix that one. You're right. You're 100% correct.
That would make me wonder. So.
Yep. This schematic is not perfect, gentlemen. You're 100% correct. Where it says switch battery bus, above it there should be a solid black line too. And if you want to put in that solid black line, that's okay. What they were using is the fact that through the essential bus relay and the switch battery bus relay, they just forgot to carry it through. Good? Good question. Good point. Anything else?
I guess the other thing to note with this, just by looking at this schematic, in order for this transformer rectifier to actually trigger that essential bus relay, you've got to have this DC bus tie in order for that to all happen.
Exactly. Also known as a cross tie. Okay? Any questions about that? All right. Now, when we look at the battery charger, in talking about the battery charger, first thing is the battery charger itself is only applicable to the NiCad battery. I'll say that again. The battery charger itself, located up in the right-hand side there in the center, a teal color, greenish bluish color box, is only going to be applicable to the NiCad battery. Now, as we look at the NiCad battery, that battery charger is going to provide for 2 things, and we'll talk about those here in just a second. But what I need to talk about before that is that goes away for the slab battery. So how is the slab battery, the sealed lead acid battery, charged? What's going to take its place is a little relay. what is now going to happen is through that relay, it's going to send power backwards through that battery, causing a chemical reaction within that battery that's going to result in charging it. Now, what is the benefit of that system versus this system that we got rid of it? With that system, there is no possible way to overcharge the battery. It can only take it to the max capacity that it can take it. Being very careful that once you put a battery in, brand new, chances are it never recharges all the way up again. Everybody understand that? That's why I'm very careful to say it'll charge it back up as far as it can. But it cannot exceed it. Where this system, there is that possibility resulting in a thermal runaway. That's why they changed it. But both batteries charge, contrary to popular belief. Okay? Because the slab battery is listed as a maintenance-free battery, people have come or induced the conclusion that the battery does not get charged except once every 3 years when it's scheduled for. But that's not true. It is constantly charging throughout the entire life of the battery. Now, the battery charger itself is actually going to do two things. By definition, one of them is what?
Charge the battery.
It's going to charge the battery. The other thing it's going to do is it's going to monitor that battery. So that's the two things it's going to do. It's going to charge the battery and it's going to monitor the battery. In charging the battery, the magic number is 80%. In charging the battery, the magic number is 80%. Inside the left electrical pod are two lights. One's marked battery charged and one's marked charging. Once it's 80% and above, we're going to get the charging complete light. But is charging complete? 80% is not 100%, is it? So what else happens? What else happens is it's going to go down to a trickle charge. And that trickle charge is going to continue to charge that battery up to the max capacity it can charge it. Any questions about that? If it's 80% and below, it's going to charge it as fast as it can. How is it going to charge it? It's going to pull 115/200 volts AC, turning it into DC and charging the battery. Which is why that battery charger circuit breaker is in the AC portion of your PDP. It is Charlie 22, which is on the number 1 PDP, bottom center. That's where you're going to find that battery charger circuit breaker. Again, that's on the left PDP, number 1 PDP. Bottom center is Charlie 22. Any questions about that? Now, what's it monitoring for? And the monitoring portion is for NiCad only too. It's going to be monitoring for an overheated battery or battery charger, short or open circuit, cell imbalance. What are all three of those going to create? Heat. Bad. So therefore, it will protect the system. Any questions about that? Number 1 and number 2 transformer rectifiers, located in the left and right electrical pods, which look just like this. They're going to take 115/200 volts AC and convert it to 28 volts DC. This is where the 28 volt DC system comes in. Okay? So it's going to take 115/200 volts AC and turn it into 28 volts DC. And you'll notice the nice thing about it is when you look at these schematics, what the AC power source is, it doesn't matter. It does it the same way each and every time. And this is where I get excited. When we talk about the DC system, from here back never changes throughout the entire process, regardless of what happens up here. So So once you understand the process, it's very easy to understand. Any questions about that? All right. Now, those transformer rectifiers provide for 200 volt amps. Why is that important to understand? How many amps does it take to kill a person? Less than 1. And you have 200 amps being created. And we will actually see people, we got you so well trained to shake electrical connections for check for looseness that you forget that if those transformer rectifiers are powered up, trying to check for looseness can get you killed. Everything you need to know is right there. And what do you need to know? One is, will these fans turn? You will commonly see people blow into them, making them turn. That's verifying that the fans are turning or free to turn. The next thing you want to check is for looseness of electrical connections. But if the transformer rectifiers are powered up, if any of those electrical connections are loose, there's going to be some type of arcing and sparking going on in there. So there's nothing that you have to shake at this point. Everybody understand that? Okay. And that's as long as they're powered up. Now, these transformer rectifiers are air-cooled from inside the aircraft. Why is that important to understand? Because people have a tendency of wanting to cram things behind those first 3-person troop seats. In doing that, that is where the vent for those transformer rectifiers are. And what will happen is those vents will suck whatever's there against it, sealing it from air being able to get in and keeping it cool. And it will result in fire. I know of at least 3 fires that we've had. So you don't want to put jackets behind there. Reverse current cutouts. The reverse current cutouts are located inside each one of the power distribution panels, up in the very top there. Now, what you're going to find out is those reverse current cutouts are going to do 2 things. Prevent reverse current by definition, but the reverse current cutouts are also what turns on and off your rectifier lights. So if power is going through those reverse currents the right way, the rectifier off caution lights will be out. If there's no current passing through them, then they will turn the transformer rectifier lights on. Any questions about that? Okay. Now, again, why is there a possibility of reverse current? Why is there a concern about reverse current? Just like in AC, electricity wants to follow the path of least resistance. What would be the path of least resistance? Back through that transformer rectifier that is shut down, resulting in the possibility of a fire. So that's why it has to prevent reverse current. DC, external power. Listen, gentlemen, the same things apply to this. But now, what do we have to talk about? We have to talk about our order of priority. The DC order of priority is your external power control, your external power unit, whether it's an AGPU, whether you learn it as auxiliary ground power unit or aviation ground power unit. Bottom line is external power source. Then it's your transformer rectifiers. And then it's your battery. It's actually 180 out from what you learned from the AC. So external power in the AC priority was the bottom. In the DC it becomes the top. Any questions about that? And order of priority will get you every time. They will ask you order of priority, guaranteed. You have to be familiar with that. Any questions? All right. Describe the power distribution system. Now, You'll notice there's like 9, 10 pages, and you're probably starting to panic here. Reality is, we've already covered it, but in order to make this very, very simplified, what we're going to do is we're going to look at this picture, and we're going to start from a static aircraft. Meaning what? We're going to pretend like nobody's had anything to do with the aircraft. We're all walking out to an aircraft for the very first time. Good? Now, what's going to happen? The first thing we're going to do is we're going to go to the left electrical pod, and we're going to plug in the battery. At this point, what's available? Hot battery bus? Switch battery bus. Are we tracking? We good? Okay, so what's the next thing I have to do to get the next bus available? I have to turn the battery on. Now what's available? The essential DC bus. Keeping in mind, did the switch battery bus go away? Nope. So the switch battery bus is still available, and so is the hot battery bus. So by reaching in there and turning on the battery switch, we now have 3 of the 5 DC systems available. Okay, so what's the next thing we're going to power up?
Generators. Or, yeah.
No. APU generator is going to be the next thing we're going to be powered up. Keep in mind, we are not maintenance pilots. Okay? We are line pilots. So all we're focused on is line pilot interaction. Okay? So now I crank up the APU. I turn the APU generator on. Now, what is available? Be careful. What is available at this point?
AC.
Be more specific, Bus.
AC number 2.
Is he right?
Is available.
That one is available. What else is available, though?
Everything should be.
Everything. So we should have number 1 and number 2 AC system.
Trick question. Yeah.
And we have all 5 DC buses at this time. Just by turning on the APU generator. Everything that we have available to be powered up is now available. Everybody tracking on that. So 5 DC systems and 2 AC systems. Now, here we go. We crank up the engines. We get to 100% rotor RPM. Generator number 1 on, generator number 2 on. And at this point, what has changed?
We're using the main generators.
We're using the main generators for AC power sources for the associated system at this point.
So the switch battery bus is off now.
Nope, switch battery bus is still available, but what's it using as a power source now, Bus?
Rectifier.
Yes, sir. The only one that did not switch was which one? The hot battery bus. Now, here we go. We're going to finalize this. You ready? That's the way the system works. So now, in understanding the way the system works, we can understand what's going to fail. But we're going to make sure that it's cleared. And here's what I like to do. My left hand, your right, is my AC power source. We tracking? We good? My right hand, your left, is now the DC system. And you notice I'm specifically putting up 3 and 4 fingers. Why? Because in the case of a DC failure without a bus tie, there's 3 lights that are going to illuminate. In the case of an AC failure without a bus tie, there's 4 lights that are going to be illuminated. Okay, what I like to do is start off at the top. The first light that's going to be applicable to both of them is going to be what? Fuel pressure. Why? Everything on this aircraft is DC controlled, AC operated. So whether we lose the AC power source or the DC is irrelevant. We're going to lose the pumps. And in losing our electrically operated boost pumps, we're going to lose our fuel pressure. We tracking? We good? Now, here's where we go. It gets a little tricky. I'm going to go down to the bottom one. AFCS. Why? AFCS is DC controlled, AC operated. Good? We tracking? We good? Now we get into these center areas, which gets a little tricky because now I have 2 over here, but I only have 1 over here. So we're going to concentrate on the one right here.
Right.
Why? Because the one that's right here is going to be right here. Excuse me, it's going to be right here. And that is your associated rectifier light. We tracking? Which means that this one by default has to be what? The generator. Why? Because the generator affects the rectifier. But the rectifier doesn't affect the generator. We tracking? Good? So now we know what lights and why. Concur? Now we need to discuss, why am I putting this aircraft on the ground? In the case of a generator failure without a bus tie, I have one underlying step, and that is land as soon as possible. And the Dash 10 tells me why I'm landing if I know how to understand it. And that is what?
Yeah. Your fans.
Your hydraulic cooling fans are no longer working. In the case of a number 1 AC failure, you're going to lose both the utility and the number 1 flight control hydraulics. In the case of a number 2 rectifier failure or generator failure, you're going to lose the number 2 flight control hydraulic pump, or excuse me, cooler. And if you have never been told, hot hydraulic fluid is the most flammable fluid you have on this aircraft. It has the lowest flash point as a vapor. Now, there's one more consideration that we have to keep in mind. And that is what? What else am I going to lose that's going to require me to get this aircraft on the ground? In losing the AFCS computer, keeping in mind, in this case, I am losing the computer. Why? Because the computer is no longer being powered up. So we are also going to lose what?
LCTs.
Yes, sir. Yes, sir. Which is the other final consideration in getting this aircraft down to the ground.
Why does it make it land as soon as possible then? Because if your LCTs are extended, you want to roll to a
Remember, we
landing
lose them
order.
all together now. It's not just automatic. We lose both automatic and manual. So we lose every bit ability to control those LCTs.
Yeah, so probably you'll be flying at 100 knots.
Well-
and they remain in the 100 knots position, and you need to do a land as soon as possible.
And this is where we have to be careful, okay? We'll discuss this one a little bit more in just a little bit. Hold on, okay? Any questions about anything that we covered so far? Okay, if not, for the last 3 hours, we've been talking about the aircraft's electrical system, its components, and its malfunctions. Any questions?